Konnichiwa. Watashi wa Godfrey desu.
Watashi wa Terence desu.
私たちは日本語が話せませんので、これから英語で発表します。すみません。
Hello, I'm Terence. I go by Hone02 on Twitter. I'm mostly known for my blue hats. I have some blue hat stickers if you want to come talk to me afterwards. I work for Heroku, like Jonan said.
Right, and in case you missed this, this is me. This is apparently how I look like. You can tell us apart by the lack of blue hat. I go by Chenko on the internet, and in case you're wondering about the picture, I do not work at Basecamp, and I guess I also don't work at Heroku. I was on the Rails core team until relatively recently, and at some point I did one of those pictures for everyone on the core team, so that's why I have it. So I actually work at a company called Tilde in Portland, Oregon, same as where Jonan is. You might know us from our product called Skylight, which is a Rails performance monitoring product, which we'll come back to in a little bit. So the two of us travel really, really far away from a land called United States of America. Just like Japan, we're known for the very delicious food we have in America. You're probably thinking about something like this, wow, this is pretty delicious. Like when it comes to American cuisine, fusion cuisine is where it's at. For example, this is what sushi looks like in America. And if you're looking at that and think, wow, like who put that much sauce on sushi? You can actually order it with even more sauce. So the reason I think fusion cuisine is pretty cool is that as a chef, you have to walk a really fine line between fusion cuisine and Confucian cuisine. So for example, this is also marketed as sushi in America, and so is this. Anyway, if you have an opportunity to go to America, I would recommend that you try them. So anyway, back to Hiroshima. Today we are here to talk about Helix, and which is an open source project we created to help you write Rust code and Ruby. So to explain why that is a good idea, I would like to tell you a little bit of backstory about this. And I apologize to those who already heard this because 2 years ago I came here to RubyKaigi with my coworker Yehudi Katz to give exactly the same talk. Unfortunately, or fortunately, Yehuda recently had a baby, so he couldn't make it this time. If you're wondering how they're doing, or if you want to send your greetings, you can follow them on the internets, the www. All right, so back to Helix. So as we discussed last time, basically I believe everyone is here because you probably enjoy writing Ruby, you probably love Ruby, I love Ruby. Ruby is pretty awesome, but we also know that Ruby can be a slow programming language. Most of the time, it doesn't actually matter because most of the workload in the world turns out to be I/O bound. For example, when your Rails app, most of your time are spent waiting for your database or waiting for an HTTP request and things like that. However, sometimes, occasionally, you might happen to end up with workload where it matters. Maybe you're encoding a video, maybe you're crunching numbers for machine learning. So occasionally, you do care about getting the most performance out of your code, and that's kind of where the pitfall of Ruby is at the moment. Now, in Ruby, there's actually a well-known solution for this. In Ruby, you can get the best of both worlds by writing native extensions. For example, when you require the JSON gem, what you're getting, if your platform supports it, is actually an implementation of the JSON gem API implemented natively in C. which is very fast, and as the user is completely transparent to you. If your platform happen to not support it, you will use the Ruby implementation, but the two are completely interchangeable, and you can't really tell from like doing JSON.parse or JSON.load and stuff like that. So this is also how the Ruby core team, using the same C API, implements classes like date or path name, where they're used relatively common in the real world, and you want to make sure they're as fast as possible. And one example of this phenomenon is a few years ago, Sam Sefrin from Discourse discovered that the string.blank method from active support is one of the hotspots for Discourse. So he wrote a C version called fastBlank as a gem that made the operation 20 times faster, and it only took 50 lines of code in C for that 20 times speed up, which seems like a pretty good deal to me. So the question is, if this is possible, why don't we do it more in general? In a nutshell, the problem is C, right? Like, we're here because we're Ruby programmers, not C programmers. If we like programming in C, we would have programming in C, right? C is unsafe, C is risky, and in addition to that, it basically increases your maintenance burden as the author of the library, and also it increased the contribution barrier for your potential contributors, right? Because now they have to be thinking in C, they have to make sure they don't make sure they're very careful around pointers and stuff like that. So a few years ago at Skylight, we ran into the same kind of problem, right? Like, as I mentioned, Skylight is a performance monitoring tool that runs on your production server, so we want that to be as fast as possible. So when we first started the company, we did what probably everyone in this room would do. We wrote the agent in Ruby, right? That makes sense, and that worked out okay for us. But eventually, we ran into a wall where to add the features we wanted, Ruby is basically getting too expensive for that, right? Like, we want to do memory allocation tracking, we want to do like maybe even CPU profiling without the overhead of Ruby. And so at first, we thought we'll solve the problem by writing a native extension in C or C++, but turned out that was not really that great for the reasons I explained previously. So in the end, we end up turning to Rust, and I'll hand it over to Terence to explain why we think Rust is a good solution for these kind of problems.
So I'm sure not everyone here is familiar with Rust, but Rust is a systems programming language similar to C, which means it emits pretty fast code in assembly, and there's no runtime that you're actually running, unlike Ruby. But unlike C, it's actually a much more pleasant language to program in. It has a much more advanced type system that lets you encapsulate a lot more kind of advanced use cases and things. And one of the neat things about Rust is that if you can get the code to compile, it doesn't crash. And so it means that we can get similar memory guarantees in Ruby without actually having a garbage collector. And so that's actually really nice. So it has this whole ownership system that helps take care of all that stuff for us. And probably one of the biggest features I think makes Rust compelling from a performance perspective is that there's this concept in Rust known as zero-cost abstractions. And what I mean by that is that oftentimes in Ruby, as you're programming along, there's this tension between actually writing this like higher level abstraction code and actually potentially writing lower level code that is much more performant in Ruby. And as an example, SF Eric gave a talk a few years back, I believe in 2014, where he highlights if you want to like iterate through the keys in the hash, you probably think, let's just write hash.keys and call .each on it. But there's actually a special method on the hash class called each key. And if you use that, it's about 33% faster than just calling it naively. And the nice thing about Rust is that you don't really have to make these trade-offs because the compiler is able to kind of do that for you. And so I think a good example of this is trying to sum the numbers in an array. So in a systems programming language, you would probably just iterate through a loop and just add up all the numbers in that array. In Rust, we actually have higher level functions similar to Ruby. So there's inject here, or fold, which is similar to inject in Ruby. And it's actually faster in Rust to use fold over doing the for loop because you're giving your intent to the compiler, so it knows not to make boundary checks as it goes through and iterates over the array when it compiles it down to assembly. So we're able to actually generate faster code than if we were to write the thing by hand. And if we go back to the fast blank example that Godfrey was talking about, this is what it would take to write fast blank in Rust. And even if you aren't familiar with Rust, I think it's pretty understandable what is happening here. We're calling a bunch of pretty high-level abstractions to deal with the characters in the string. But this isn't totally fair. If we look at this snippet here, the code on the left is the code in C, and the code on the right is all the code we need to write in Rust to make it work with Ruby. And the stuff in yellow is basically all the interesting bits that you actually need that isn't boilerplate. So on the right, that small snippet is the code that we had on the previous slide and over here. And if you look, it's basically about the same amount of code to actually get it working. And so this is one of the big reasons we want to build Helix, was to kind of remove all this boilerplate. So in about 12 lines of Rust code, we're able to write the equivalent thing without basically that 50 lines of Rust to get it working with Ruby.
Right, and I guess I will jump in and talk about the vision of the project quickly now you know how to use it. Right? So I think our vision for Helix is that like you should always basically start by writing your code in Ruby, right? Like most of the time the performance benefit doesn't actually end up mattering, but you can do this without the fear that you'll eventually hit a wall and forces you to rewrite your entire app in, like, I don't know, like a bunch of Go microservices or something, right? So the idea is you can start with Ruby, and piece by piece you can move the performance-sensitive code to Helix and native extensions as they become appropriate.
So now we're going to take a look at a demo. If this is up here, Godfrey did a nice telecast, I guess, of it at this URL. So if there's anything you miss, this is just going to be kind of the highlights from that demo for time reasons, so we can talk about some other things besides just going through the code. So the demo that we're going to be doing is a simple text flipper app. It's a Rails app. And so if you input some English and then you click the flip button, you get some Australian back. And so you have that there. And so since this is a Rails app, Helix actually provides some generators. So the Helix Rails gem, you can call a generator like you would in any other kind of Rails generator, and actually creates two special files that are specific to the Helix crate. So it is both a Ruby gem and a Rust crate. So you get all the standard Ruby stuff, but you also get this cargo.toml file, which is basically the equivalent of a gem file in Rust. So that's where we specify all your dependencies. And then librs is kind of the main entry point into your Rust code. So as part of that, this is kind of just the simple hello world example that is automatically generated. And it does what you think it does. It prints hello from text transform out onto the screen. So if we go ahead and load up IRB for Rails, we can actually see it go and compile and pull in the dependencies that we specified in the crate, and then we see it actually prints out that text for us by just calling it like we would any other Ruby code. And so since we're doing stuff in Ruby, we can test the Helix crate as if it was just Ruby code, because it is a native extension. So this is us writing simple text flipping stuff in RSpec to basically have that tested against. And if we run the tests against the current code, the tests fail because we haven't actually implemented anything like the flip method. So if we go ahead inside of this kind of Ruby bang macro here, we'll go ahead and replace that hello method and write a flip method here. So all we're doing here is really just a simple mapping of characters. So when we have your stand-up, straight-up characters, we basically flip them to the upside down, and we kind of iterate through that entire list. And And so if you notice here in Rust, we're actually able to call pretty high-level things similar to Ruby, like we're basically splitting, getting all the characters, we're going to reverse it, and then call map, and map functions like it would in Ruby over some type of collection. And then at the end of it, once we've done that transform for every single character, we can go ahead and just collect that collection back into a string to then return back to Ruby here. I can go back, I guess, 2 slides. The other thing to note is that we actually have typing information. So we are specifying a type string here. And so if you actually, so the native extension will actually return a type error exception. So if you try to pass a fixsum in, we can get that kind of high-level static typing information that apparently everyone really loves. So going on, we run the tests, and we see that they pass because we've now implemented the flip method. But of course, flipping isn't complete without actually doing table flipping. So let's add those tests in here. And then since it doesn't exactly map to our thing, we're just going to add a special if case statement at the top for those special characters. And then if we run the tests after doing that, we should see that the tests pass. So now that we have basically a functioning Helix crate here that we can use inside of Rails, we can just actually call the flip method like it was any other Ruby method on the parameter input of the form that we're using. And then we should be able to see that result when we run it. So this is the example of us deploying it to Heroku. So you can take this exact code and deploy it. So we create a Heroku app. But since we're using a crate, we need to add a Rust build pack here to actually compile it. And then, of course, since we're using Ruby, we add the Ruby build pack that if you used Heroku before that you're familiar with. And then with that, we can actually push this to Heroku. And you can see it installs the Rust toolchain by running the Rust build pack first. And then after that, it goes to the normal Ruby setup. So it sets up Ruby, does bundle install, and then it automatically goes ahead and then runs cargo build through it. So you don't have to set any of that up yourself. It's automatically handled for you. So it downloads and compiles the cargo dependencies for you and then finishes setting up your app so you have it up and running. And so if you go to helix-flipper.herokuapp.com, you can see it actually flipping stuff. Yeah, so that's the demo. And so with that, you should have enough information to actually go ahead and use Helix on your apps.
And in case you missed it again, like this is the actual video with English subtitles, so you can go watch this later if you want. And there's more information, documentation, stuff at usehelix.com. So that's basically everything you need to know to use Helix. And I would like to transition in talking about some of the implementation details, because not that you need to know it to use Helix, but I think some of you here might be interested in those kind of things. So I would like to frame this in terms of like some of the challenges and solutions that we did when building Helix. So the first challenge is to make it really easy to use, right? If you're already writing C extension, if you're already comfortable with C and C++, you probably don't have a lot of reason to immediately switch to using Helix. But the whole point of this is to enable more Ruby programmers to do that, even though you're not comfortable, you might not be comfortable, thinking C and dealing with all the caveats that come with C programming. So it's very important for us to make it as easy as possible. And the problem is, if you look at the Ruby C API, it's actually pretty different from the Ruby that you're used to writing, right? So on the left, here is a simple class that has a single class method. And on the right, this is how you would do it in the C equivalent code. So this example is not so bad, but you can already see that it is very imperative, right? Like it's not as declarative as the thing on the left-hand side. And there are a number of opportunities for errors here, right? Like you actually have to say how many arguments your method take and so on and so forth. So this is the basically simplest possible hello world example. And what if you want to move the method to an instance method? Let's say you take the name and then constructor, and you want to use the instance variable later. This is the C code you would have to write to make it work. If you're familiar with the C API, you know that you have to use the data star struct API, like in this case, the data wrap struct, or data mix struct API, and you have to make sure you implement the mark and you have to implement the mark function correctly, so you mark any interior Ruby references you hold, so your program doesn't crash. And that is still a very basic hello world example, right? Like, we're not really doing anything useful yet. What if you want to write like even something as simple as a 2D point where you just hold X and Y? The code to do that would not fit on the slide, so it didn't even bother. Fortunately, these kind of problems have a well-known solution in the Ruby community, right? Like, usually when something like that comes up, the solution is to create a DSL around it, right? Like, we have rake, we have RSpec, we have even your gem file or gem spec, right? Like, a lot of times we just want to express what you're trying to do without worrying too much about the details, and DSLs are great for that. So just as a reminder, this is how our DSL and Helix work, right? So this is the first example we saw where you just want to define a class method. So if you ignore the macro implication on like line 1 and 7, it's basically exactly the same amount of lines with some mixture of types and curly braces. And this is the more involved example, which requires using data wrap struct and custom mark function and stuff. And you can see here we are defining the struct inline inside macro, and later you can access the self.name as if it is an instance variable that you have. So we think this will feel pretty familiar to most Ruby programmers. And finally, this is the point class that we couldn't fit on the slide before. And you can see, like, I won't go into much of the details, but you can see the Ruby code is 21 lines and the Rust code is 35 lines here. So it actually scales pretty well. So we know what we want to build, right? Like, so this is the DSL we want to build, but how do we do it? Our first instinct is basically to write our own parser to do it. For context, Yehudi and I work on other projects like such as Glimmer, which requires parsing handlebars and HTML intermix, so we're not new to parsers or anything. But in this case, we need to switch back and forth between parsing two pretty different languages at the same time, and even just finding the boundaries for when you want to switch into the other context turns out to be pretty complicated because, for example, this is a pretty extreme thing lifted from a blog post called Rust type system is Turing complete, right? Like, basically, it doesn't really make sense. You're not going to actually do this in practice. But if we sign up to write a parser to parse Rust, we would have to be able to handle these kind of situations. So that failed pretty quickly. So we decided we need something that already more or less understands how to parse Rust. And thankfully, that already exists, and that's basically Rust macro system. If you're a C programmer, you're probably familiar with the name macros at least. However, they're actually pretty different in C and Rust. In C, macros are basically a very simple text substitution. You basically do something like a search and replace in your source files, and then you feed that into the compiler. In Rust, the macro system is actually based on pattern matching, and it actually runs after the tokenizer, and like, it technically runs at the same time as the parser. But the implication is that you're actually dealing with already parsed Rust tokens instead of raw text. So to show you how that works, this is, let's say this is a pure Rust struct that we did, right? So you can see if we want to have getters for the X and Y fields that we have in the struct, we have to basically write a lot of boilerplate code, and it would be nicer if we can do something like Ruby where we can just generate the getters with attr reader. So let's do that. The first thing we're doing is basically defining a macro called attr reader. And as I mentioned, the macro system is based on pattern matching, so we're going to match on the parentheses around it. And then the first thing we're expecting is a struct name, which you can just ask for, like, I want this to be an identifier, and the compiler is going to reject anything that is not a valid identifier for you. And then that's followed by comma, and then we want to match on a field name, which also happens to be identifier, followed by colon, and then we want a type. So again, because this actually runs at the same time as the Rust parser, you can just ask for a type, and it will try to parse the token as a type, and if it fails, it will reject it. So after that, you can basically just write whatever code you would have wanted to write with the variables in there. So let's build on that a little bit, and it would be nice if we can combine the two adder reader call on line 6 and 7 into a single call, something like this, right? So if we want to implement that, unfortunately, it is not going to match our the rule, the pattern matching rule that we have defined previously, because now we have something extra, comma y colon f64 in there. So to fix that, we basically introduce another pattern. I basically copied the first 3 things that we expect. However, I allowed comma followed by arbitrary syntax, which allows us to recursively call back in the same macro. So we can handle the first thing in the thing, and then we can like recursively handle the rest. So that's a quick tour of the Rust macro system. What follows is the TMI section, and thank you, Julian, for the translation. So if you don't understand any of the stuff that comes next, don't worry about it. If you're interested, we can talk in details after the talk. So the Rust macro system is pretty nice because you don't have to worry about like a lot of like tokenization parsing and stuff, but it does come with some restriction. The first thing, it has a recursion limit, which we'll talk about next. It also has some, it is a hygienic macro system, if that means anything to you, but it is also occasionally quite annoying to work with that kind of system. And finally, because it runs after or run at the same time as the parser, it is required that each macro expand into valid Rust syntax. So that, actually, we'll come back to that. So let's talk about recursion limit first. So this has a pretty simple solution. Turns out you can just increase the recursion limit, and as far as we can tell, nothing bad really happens. It's like the U limit on OS 10, no one really knows why it's set so low to begin with. However, that does mean, annoyingly, you would have to type this in your source file to successfully use Helix most of the time. But at least there's an easy solution there. The second problem is a little bit more elaborate. So as I said, the Rust macro system requires each expansion to expand into valid Rust syntax. That in practice means that a lot of times if you want to break down your macro into smaller macros, and it basically makes it impossible a lot of times, because a lot of times you basically have a partial result that you want to hold on to and do more stuff with it, and you can't really do that, as you can see. So turns out there is a solution to this. So as you can see, because a macro invocation is a valid Rust syntax, and you can basically pass anything to a macro, you can always expand yourself into another macro invocation. So that turns out to be enough machinery to build a thing called a pushdown automata, which is a fancy state machine that uses a stack to carry forward information. And again, this is probably TMI, but this is roughly how the Helix parser works in the macro system. So you start at a state called top level, and you have 2 choices. If the buffer is empty, then you know you're done parsing. You can just pass the AST to the codegen macro. Otherwise, if there's anything in the buffer, we basically switch into another state called parse class. I guess I lost that slide, but oh well. We basically switch in a state called parse class, and then Anyway, we're basically expecting the class keyword followed by name, blah, blah. And so here we'll take information off from the stack, and then we'll go into another state called parse struct, and then we'll carry over that buffer information, etc. Interesting. Here they are. So that is the TMI section, and the more of the story is it turns out you can always do that to parse basically arbitrarily complex grammar. You can even push stuff back into the buffer to emulate backtracking. So we are going to jump through this very quickly. So the second challenge is type safety, right? So let's look at the Ruby C API. Here's some selection of the Ruby C API. As you can see, this thing called value is everywhere, so what is it? If you look at the header file, it is a unptrt, and that turns out to be basically the same thing as a void pointer. So the more of the story is everything in the C API is basically a void pointer, so the compiler is not really going to help you if you accidentally pass a string to where a class is expected, and you can cause who knows what kind of problems. Rust has some pretty awesome guarantees we talked about before, and I want to focus on how the zero-cross abstraction can help us here. So again, this is how you define the value pointer in C. This is the equivalent in Rust, so you can do it. However, it's usually more idiomatic to do this, which is actually a shorthand for that. Basically, that make a new kind of struct called value, and it holds exactly one member, which is the void pointer. The thing about this is because the size of the struct is the sum of the members, this actually has exactly the same memory layout as the void pointer itself. However, this creates a new nominal type, so the compiler is not going to let you accidentally pass the wrong thing around. And so that's pretty great, but what if we want to remember what we stored in the value in the first place? So there's a type in Rust called phantom data, which actually has the size of 0. So if you do the math again, you realize this still has exactly the same memory layout as the void pointer itself. So there's no runtime cost, but now you get a slot to hold a generic variable to tell the compiler what this value might be. We use this feature in our coercion protocol. So this is the example we saw before. If you call it with string, you're going to get it to work. If you call it with number, it's going to fail. This is how we do it. So this is roughly what the function we generate for you, right? So you take a value. So first thing, you're not taking void pointers anymore, so that's an improvement. And then we are going to call a thing called toChecked, which returns either a check value, which we saw on the other side, like either a check value of string or an error. So this is the implementation, if you want to look at it. And so then we can match over the result, and either we get a check value of string or we get the error. And if you get the error, we just raise it as a Ruby exception. Otherwise, we call to Rust, which gives us a string. Thank you to the phantom data thing we saw earlier. And this is the implementation. And finally, so the thing to call it here is you're working with the check value of string, which, if you remember, is basically the void pointer. However, you now don't have to assume that you have to deal with any kind of other kind of value. So by the time you actually use it in your code, everything is already type checked for you, so you don't have to worry about it. Same thing for the return value. I'm going to skip that. And this is how it generalized to n arguments, basically. I'm going to upload the slides so you can read that part yourself, and I'm going to let Terence talk about distribution.
So in the deployment example, we had to add a Rust compiler into the Heroku build system, and that's fine. People have system dependencies or other things all the time when you're deploying stuff, but it's not really ideal. Not everyone has the freedom to kind of just control their deployment build pipeline. In addition, it also increases your bundle install time. So when you're compiling stuff like Nokigiri, it actually builds all of libxml too, and family and friends, and that can take upwards to minutes. So similarly with Rust, when you compile and link, it can potentially take a long time depending on how big your Rust program is. So if we can do anything to kind of minimize that, that would be great. So another example in the Ruby ecosystem is the libv8 gem. So this is basically running the V8 engine, so you can use it, interface it with Ruby. For example, the Ruby Racer. And it takes a really long time to actually build it. So to actually do that at build time when you're deploying your app would be pretty terrible. So, and also Google has their own kind of build system called JIP that requires Python 2.7 to do it, which may not be a dependency that everyone necessarily has as the world moves forward with Python 3. So what they've done, they have actually pre-compiled the V8 binaries. So if you look at rubygems.org, you can see for a single release, there are many releases, but it includes pretty much almost every major platform that people would want to install it for. And this means you're able to kind of circumvent and cut through and not have to build V8 from scratch when you depend on this library. So we want to have a similar story when you're building Helix crates as well. And so one of the first things we looked at was trying to do cross-compilation. So being able to, like the Go tool chain, which is take it from your computer and build multiple operating system binaries for your Helix crates / gem. And Rust has pretty good multi-platform and cross-compilation support. As we've seen, since Rust ships with Firefox now, it actually works on multiple operating systems, and it's had to work pretty well. But unfortunately, Ruby's story is not that good with it. So we abandoned this direction relatively quickly for now. And so we're actually just going to use basic machines in those operating systems to actually build the binaries. So this pattern has been used before to basically leverage CI. So for Linux and Mac, you can use Circle or Travis to kind of run your tests / build to build those binaries. And then for Windows, we can use AppVeyor, which is built on top of Microsoft Azure. And with that, we can actually go ahead and have binaries that we can publish. So if you're doing basically this native extension compilation inside of your gem spec, you have to actually change gem spec platform to be the local one, so it knows to not just use Ruby, which is the default one that most Ruby gems use. And then we opted to go with a Ruby script here to actually publish it, so it works on both Windows and all the Unix OSs as well. And here is the code that you need to actually like write out your RubyGems credential to actually publish it to RubyGems as well. So with that, we can generate a bunch of config for people to actually go ahead and publish those things to RubyGems. But unfortunately, we ran into some hiccups with 32-bit Linux. Travis and Circle don't actually offer to the public anyways 32-bit Linux containers, and they recommended using Docker images, but Docker also doesn't have like an official 32-bit Linux thing, and so, but you can build a 32-bit container that is specific, but we actually ran into some segfault issues with the linking when we tried to require it, so this is something we're still investigating into. Yeah.
Right. So there is a roadmap of what is it good for today and what it could be good for in the future, but like it's actually on the website, so I'll just let you read it on the website if you're interested. Website is usehelix.com. And finally, I want to talk about some of the ways that you can help. The best thing is probably to try it and let us know what you think. You might not be able to do exactly what you need to do right now, but like having some early feedback would be very important. And also, since we're here, we can also hack on the code together if you want, like tomorrow or the day after tomorrow. We could use some help on like debugging these Windows or Linux 32-bit or linker issues. So if you're familiar with that, we would love to chat with you about that. And also if you have experience cross-compiling Ruby, that would be very useful as well. And finally, if you don't want to work with the technical stuff, and if you just tried Helix and then you think the documentation is not as clear as it could be, we could use some help there as well. And finally, Tilda is a consulting company, so if you happen to need to write some Rust native extension, we could probably help you out and also improve Helix along the way. So that is the end of the talk, and we're out of time. So thank you very much arigatou gozaimasu.
Talk about the text transform gem.
Also, you can run gem install text transform on your computer. It would install the text transform gem natively without having to have the Rust compiler on your machine, thanks to the CI setup that Terence did.
So apparently, do people have questions? Do we have time for questions?
I guess not.
I guess not.
All right, we will be around. So if you have if you tried tonight and you have feedback, questions, whoa.
Oh, we do.
Okay.
There's someone. I wondered if you guys had entertained the idea of developing a macro to do Ruby-style string interpolation.
Sorry, in what context?
Instead of using Rust's curly brackets to actually support pound curly bracket, name curly bracket.
I believe the current macro system is not sufficient to do that kind of stuff because a string is always parsed as a single token in the macro system today, so we cannot take apart the string. I think in the future there will be a more imperative API called procedural macro, so you can potentially then do more, like you can actually write Rust code to do transformation there in the future.
Thank you.
Apparently we have time for one more question if there is one. Set.
My question is about maintenance of code because Rust development is very active, I think.
What was the question?
What was the question?
Maintainability of the Helix or Rust compiler or something. Sorry.
So the question is, how is the maintainability of Rust code in general?
Yeah.
So Rust actually takes stability very seriously. So zero cost abstraction is the thing we talked about here, but Rust actually have free so-called marketing headlines, right? Like the first is zero cost abstraction. The second one is stability without stagnation. The third one, I don't remember, you can look it up from the website. But what it means is they have hit 1.0 like 2 years ago, I think. And since then, they've only been doing minor versions in like backward compatible way, assuming you're not using private APIs and stuff. So in theory, and also we currently do not use nightly anymore, so we're completely on Rust stable. So in theory, the code that you write will work in all of Rust 1.x, and I don't think Rust 2.0 is anytime soon on the horizon. So it is pretty active, but all of the features are additive. So it is not supposed to, if the Rust compiler upgrade broke your code, you basically should report that as a bug and it will be dealt with accordingly.
Okay, thank you.
Thank you.
Thank you so much.